direction of the current due to that conductor in that magnetic material. So using Fleming's right hand rule, we can easily find out the direction of the current in any way wherever your conductor is moving in the magnetic field. Now one of the example of the Fleming's right hand rule is
Fleming's right hand rule. When the thumb, the forefinger and the center finger of the right hand are stretched mutually perpendicular to each other and are held such that the forefinger is along the direction of magnetic field B and the thumb is along the direction of motion M of the linear conductor, then the center finger points along the direction of induced current I or electromotive force. Consider a rectangular coil ABCD placed in a magnetic field B due to horseshoe shaped permanent magnet Sn. If the coil is rotated in anti-clockwise direction, such arm AB moves upwards or CD moves downwards. The induced current will appear from A to B in the arm AB according to Fleming's right hand rule. Similarly, in the arm CD, the current will be from C to D. Thus, Fleming's right hand rule helps in determining the direction of the induced current or electromotive force.
So here we sees that whenever any moving conductor can be placed between the two magnetic material, then that conductor when moving towards either the clockwise or the anti-clockwise, it cutted the magnetic field of that particular magnet. So when we have to find out whatever the direction of the current due to that cut the magnetic field, we can easily find out from the Faraday's Fleming's right hand rule. Now the hysteresis. When we are talking about the B magnetic field and the hysteresis, then you can find out the hysteresis loop of that particular material. Now what hysteresis says, that hysteresis depends upon the system not only on its current environment but also on its past environment. So you have to take just one of the environment as a reference and talking about the current environment. The dependence arises because the system can be more than one internal state. That one is happened due to that the hysteresis not depends directly upon the present or the past. So you have to consider the both the environment, and now predict its future development. Either its internal state or its history must be known. This is called as a hysteresis curve, where you just kept the magnetization and applied magnetic field, so M and H. So here that the graph shows that the B by H, that is called as a magnetic hysteresis loop. So this is very important hysteresis loop curve in the field of magnetization. Now the next one, that is the magnetic fringing. The magnetic fringing is also says that whenever the two magnet materials are placed some distance with each other and any moving conductor is rotate between that, then the amount of magnetic fields are cut. So here the dotted line are known as the magnetic fringing due to that magnetic flux generated by that magnet. So the amount of magnetic field can be defined from the magnetic fringing whenever we are placing any conductor which clockwise movement or which has the clockwise movement or the anti-clockwise movement, and it cut it down the magnetic fields. The next question, that is the question number 3a. Whenever the two capacitors when connected in parallel and the series, so the measures the value of that capacitance. The capacitor value is the 16 microfarad and the 4 microfarad. So we have to just find out the individual capacitor value first in a series form or in a parallel form. Here just we see that the two capacitors are connected in series form. This is the first capacitor C1 and C2, 16 microfarad and 4 microfarad. This is in series connection, and C1 and C2 are in parallel form, so for individual circuit we have to just find out the equivalent capacitance. Here the C1 equation of the for the series capacitance is C1 into C2 upon C1 plus C2, whereas for the parallel circuit the equation becomes C1 plus C2. So now substitute the value of C1 and C2 into that particular equation, we just get that this is the formation of equation in series form, C1 1 by C1 plus 1 by C2. So we can directly write that CE equals to C1 C2 upon C1 plus C2. This is the equation. This is the configure of two series capacitor, 16 microfarad and 4 microfarad, and ultimately CE equals to C1 is 16, C2 is 4, so 16 into 4 by 16 plus 4, so 64 by 20. So we can get that CE equals to 3.2 microfarad in series connection. See that series (16 into 4 upon 16 plus 4), ultimately 64 by 20. So with solve using the mathematical equation, we get that 3.2 microfarad whenever these capacitor are connected in series form, and if they are connected in parallel, then C1 plus C2, so 16 plus 4 microfarad, it means that 20 microfarad whenever they are connected in parallel form. Now this is the parallel plate capacitor. We just briefly give the overview of that. C equals to C1 plus C2. This is the general equation of the parallel capacitor. Whenever you are connecting more than one parallel capacitors, so you can just find out that C equals to sigma I to N Ci, where I is your number of parallel plate capacitors. So if 4 capacitors are connected as a parallel, then the equation becomes C1 plus C2 plus your I equals to 4. So ultimately C equals to C1 plus C2 plus C3 plus C4. So this is the just general equation. Here we get that C equals to 16 plus 4, that is 20 microfarad. Now the summary, that is the summary of the circuit, the series and the parallel. See, 1 by C is general equation, sigma I equals to 1 to N, where 1 by Ci. So again, if there are 3 series capacitor, then the equation become 1 by Ce equals to 1 by C1 plus 1 by C2 plus 1 by C3. In a charge, that is Q, in particular capacitor, they are all the charges are in series capacitor are equal. So you can find out that the Q equals to Q1 equals to Q2 equals to Q3, and the Q equals to CV, and voltages are the summation of all these capacitance, that is V equals to V1 plus V2 plus V3. So this is the equation for two capacitors, C1 C2 upon C1 plus C2. Now same thing for the parallel plate capacitor, that C equals to sigma I equals to 1 to N Ci, and the Q equals to, now here the Q and the V are the inverse in the series form, where in a series form the charges, all are the charges in the capacitor are same. So here the voltages in parallel are same, as we all know that the voltages in parallel circuit is the same. So V equals to V1 equals to V2 equals to V3. All the voltages in a parallel plate capacitor are the same, but the charge according to all the capacitor is different, that it is the summation of all the series connection capacitors. So the charges in C1 capacitor is different than the charge in C2 capacitor.
On the left side, I have two capacitors connected in parallel, C1 and C2. I want to replace these two capacitors with one equivalent capacitor that I'm calling C sub EQ. let's presume that initially all the capacitors have no charge. And I'm going to add some charge. I'm going to add 1 coulomb. And I will develop a voltage V. On the equivalent capacitor, I'm going to do the same. I'm going to add 1 coulomb of charge and develop a voltage V. Since the capacitors are equivalent, the voltages will be the same. When I add the charge to the left side, the charge, some of it will go on to C1 and some of it will go on to C2. The larger capacitor will consume most of the charge. So let's see if we can derive an equation for the equivalent capacitor. Now recall that the charge on a capacitor Q is equal to the capacitance times the voltage across the capacitor. So the charge on C1 I can write as C1 V. The charge on capacitor C2 I can write as C2 times V. The same voltage appears across C1 and C2. For the equivalent capacitor, I can say CEQ times voltage is equal to the charge on CQ. So the charge on C1 plus the charge on C2 is equal to the equivalent charge on CEQ. Now notice that the V's cancel. I'm left with a very simple equation. CEQ equals the sum of the parallel capacitors, C1 plus C2. So for capacitors connected in parallel, to get the equivalent capacitor, you just add the two together. Let me erase this. Now let's do the same thing for series capacitors. On the top I have C1 and C2 connected in series. I'm going to inject a current of 1 amp into the left side for 1 second. And below I have an equivalent capacitor that replaces C1 and C2 with one capacitor called CEQ. And again, I'm going to inject 1 amp for 1 second into CEQ. Since they are equivalent, I will get a voltage V at this terminal and the same voltage V on the capacitor at the bottom. Now note that as I inject this 1 amp for 1 second, I get current flow into C1 and out of C1 into C2 and out of C2 into ground. So the same current flows in C1 and C2. So the same charge accumulates on C1 and C2, which I'll call Q, and Q on C2. The same thing happens to CE equivalent down below. I run 1 amp for 1 second and I develop a charge on CEQ. So all the capacitors receive the same charge. So let's see if we can derive an equation for the equivalent capacitor to C1 and C2. Now, let's recall that charge is equal to the capacitance times the voltage across the capacitor. So the voltage across C2 I'll call V2, and the voltage across C1 I will call V1. So the total voltage is the sum of V2 and V1. So the V is equal to V1 plus V2. We can solve the top equation for voltage. If we do that, we get voltage is equal to Q divided by capacitance. So let's replace V in this equation for the CEQ. So in that case, I have the voltage charge divided by CEQ, and that's equal to the V1, which I can write as Q divided by C1 plus the voltage V2 that I can write as Q divided by C2. Now notice that the charges all cancel out, and let's scroll down a little bit, and I'm left with 1 over CEQ is equal to 1 over C1 plus 1 over C2. I can solve this for CEQ. CEQ equals 1 divided by 1 over C1 plus 1 over C2. Now I can multiply the numerator and the denominator by the same value, and it won't change the equation. So let's multiply the numerator by C1 times C2, and do the same thing for the denominator, C1 times C2, and I get C equivalent is equal to C1 times C2. C1 will cancel, I'll be left with